Let's take a look at some high-speed serial signals on an oscilloscope. I've got here a high-speed serial signal. We're capturing 1,000,000 points, and you can see it is edge triggered. And as we're going through here, I'd like to stabilize this so I can kind of take a look at some certain patterns. So I'm going to draw a little box on here, and I'm going to draw a box, and I'm going to add a visual trigger area. This is an option you can add on a Tektronix oscilloscope. Right now it's looking for channel 1 to go through this box. I'm going to right mouse because I want to see when channel 1 stays outside that area. So this gives me a visual trigger where I can now stabilize this, and you can do 8 of these areas and you can set any shape you want in the area. The other thing you'll notice is when I go to click on this, I can click and change the size. The actual volts and time pop up. Tektronix ties this to the data set of the scope, not to the display. So if I change scales, this is still valid because the data is still the same values. So one thing you want to do whenever you look at a high-speed serial signal is you want to capture a decent duration. You'll notice all oscilloscopes now have long records. So we're going to do a 1,000,000 point for a demonstration, but if you're doing debug on your systems, you may need to do 20 or 50 million point records to capture the low frequencies. 1 over the duration of your capture is the lowest frequency you can see. So when you're debugging, you need to keep that in mind. Let's go ahead and do some jitter measurements on this signal. I really like to see the long capture so that I can see if there's outlying signals or changes in there, or if there's some modulation. Sometimes you'll see it in here. And then you need to be zoomed in so you can look at the bits. So when doing jitter, you need a long capture. You want to look at the details of the bits, and we'll go through some of the more things you want to see. Jitter and eye analysis, DPOJET, is our tool we use for our jitter and eye measurements. It's all combined into one tool. I can do 99 measurements simultaneously in this tool. Right now I'm looking at one channel, but I could have all 4 channels up, and I can do all of the measurements we're going to do on those 4 channels simultaneously if I so need to. So very flexible tool set. If you're an advanced user, you're probably going to start out and select, and you're going to go straight to picking out what you want to do. If you're not an advanced user, and I'm going to show you as if we're not all advanced users, we can use one of these wizards. The one-touch jitter does everything for you. You pick it, it sets the scope scales and does everything and gives you numbers. If those numbers look good, chances are your system's fine on that signal and you need to go debug other areas. If it's not, that's a good starting point to then utilize the flexibility of DPOJET. I'm going to grab the serial data jitter wizard. We're going to go for jitter numbers. I'm putting in a PRBS 7, which has a 127-bit repeat. I'm on channel 1. I'm not going to have it scale the things, although I could because I've already got it scaled appropriately. And I'm going to go ahead and let it do all those plots for us. So it's going to capture that 1,000,000 points. It's going to come through, do analysis for it, and we're going to get total jitter, random jitter, deterministic, periodic, data dependent, time interval error, and DCD, duty cycle distortion. If I take a look at the numbers alone, I really can't tell much as far as if I have a set of numbers I'm looking to compare against, that will tell me if they're small enough. But looking at them alone sometimes can be misleading. So if we look at them, let's just take a look. Duty cycle distortion, sub-picosecond. I've got good balance on my signal. My time interval error is in the attoseconds, so it's very tiny. Duty cycle distortion, or data dependent jitter, sorry, has about 3. We are putting in a PRBS 7, so you would expect to have some data dependencies on the different bits. The periodic jitter, some will call it sinusoidal jitter, is quite a bit larger. It's 3 times what the duty cycle is, so that kind of is telling me there's something up. Also, I know that my total jitter, I expect this to be smaller than 12 to meet the numbers I need to qualify for, and it's up at 18, so there's something up with this. Luckily, DPOJET is very flexible, and just even through that wizard, it gives us these 4 plots. If you look at the time trend, you can see there's something modulating pretty cleanly through here, so you can see that modulation. It's a fast enough modulation we didn't see it in the overall waveform trend, but we're able to see it in the time interval error trend. You can also see there's a distribution starting to shape up in the histogram of the time interval error. One of the more telling plots is the spectrum. If you see the left-hand scale be a larger set of numbers and there's a lot of empty black space, there's usually something hugged up against that left edge. So if I click it, it'll highlight orange, and now I can zoom in on that lower edge and see if anything's going on in here. And so we see that at just over a megahertz, we have a single spike of interference causing our edges to not be in ideal locations. When you're looking at jitter numbers, you need to realize that your jitter numbers are only as accurate and as appropriate for your standard as the clock recovery. So what we need to do is we need to check the clock recovery out. So the clock recovery chosen by that wizard just put in a constant clock mean. What that means is it takes the mean frequency of your data signal, creates a software clock at that mean frequency, and that is now the reference for the clock recovery. So it goes out and checks every one of my edges relative to that reference and tells me if it's early or late. That is what time interval error is. That is the basis for Tektronix's spectral method. Tech holds the patents on doing spectral jitter separation, and we're the only ones that measure jitter. Everyone else has to use models because of the patents we hold. So you'll see different talks of different people using these different methods. They may call them spectral, but they're still modeling because we hold the patents on doing this direct measurement. So for a signal like this, we probably should be having a PLL. What you want to do is you want to set this PLL to be the same as the receivers in your system are going to use. If you don't know what that is, a golden PLL is a good place to start. So being a high-speed serial signal, I'm going to go for a type 2. I'm going to set the loop bandwidth to a golden PLL setting, which is bit rate divided by 1667. In this case, it's 15 megahertz. I'm going to apply that to all of my measurements. DPOJET is so flexible, I could do this measurement multiple times and have different clock recovery on for debug, and it's a great debug tool. I can have different settings for each of these actually. One thing before we leave the clock recovery is, again, Tech holds the patents on software PLLs for this, so we have the textbook version of loop bandwidths and JTFs, and what they've found in many of the standards is everybody was setting clock recoveries in the scopes to similar values, but because Tech holds the patents, the response of the quote-unquote PLL, the clock recovery, was very different. So many standards have started telling you what the jitter transfer function should look like. In a Tech scope, you just get to pick the jitter transfer function, dial it into what the spec says, and you're set. Because again, we hold the textbook versions. The other guys, you have to figure that out. So with running that clock recovery, let's go back and look at our results. Now we changed the clock recovery, so all of our results have been wiped out. Very convenient in DPOJET is the ability to recalculate. I want this same piece of data because I don't want to change multiple variables while I'm debugging. So right now I've only changed the clock recovery. So recalculate reprocesses the data that's already in the scope. It may have taken you 3 days to capture that error, and you want to do jitter analysis around that point in time. So if we look at this now, see, now my total jitter number is down sub 11, and my periodic jitter is down from 10 to all the way down to 2.5. And notice in the time trend we don't see that modulation anymore. Let's go back to our spectrum plot and scale this back out. Now if we scale that to 100%, notice that my scale is no longer in the picoseconds on the sides. I'm down here in the low femtos, and there is some small things going on down here, but I don't have any distinct point driving that out. Let's go back and look at where that 1 megahertz was at. So remember, we had a 1 megahertz before. And that 1 megahertz is now there, but it's been suppressed by that clock recovery all the way down to 50 femtoseconds. So by turning on an appropriate clock recovery, my numbers came in line. I got out of this. Now in my system, if I knew what that 1 megahertz was, that's good. I can go figure that out and clean it up. But in reality, the receivers are probably going to track and discard those low frequency contents anyway. Depends on what you're trying to do, if you're trying to be compliant or debug. And this tool set is flexible enough to give us all those. Now the other thing that we're missing that you really need to have when you're looking at any type of jitter numbers is, again, remember your jitter is only as good as your clock recovery. How do you tell if your clock recovery is doing its job and tracking out those low frequency things without being an expert and digging into these spectrals and trends and things? An eye diagram tells you that. Right now this bathtub plot is not providing us a lot of useful information. So I'm going to go and I'm going to choose to turn the bathtub off, and I want to see an eye diagram instead. So now I have an eye diagram of this signal. If my clock recovery was not set appropriately, this eye diagram may walk around and not stay open. That tells you that, hey, your clock recovery is not tracking whatever frequencies are causing your edges to be non-ideal. So ideally, when you're looking at any high-speed serial, you want to see a long capture. You want to see the bits because you need to see what these bit shapes look like and see if they have decent signal integrity. And you also want to see this eye diagram. And I can see all three simultaneously in addition to these other debug tools. If I want to see the eye diagram larger, or any of the plots, I can hit the plus sign. And so now I have a big eye diagram. I can put masks in here. I've got the waveform, long duration to look for outlying signals, and I've got the details of the waveform to look at what the bit shapes are. The combination of this gives me the ability to debug any high-speed serial signal out there. Let's find out some more information about the one we have here and find out what are we really looking at. We haven't talked about bitrate or anything else yet. So let's go in to the jitter and eye tool and look at all of the things DPOJET can do for us. We looked at a basic set of jitter measurements. Now this tool can do 99 measurements, so we can turn on multiple things simultaneously. I'm going to turn on frequency. And since this is a data signal, DPOJET's going to know that, and it's going to measure the data frequency, and it's going to show us what the bit rate is. The other thing I want to do is I'm going to turn on another TIE measurement because I want to show you doing multiple measurements with different configurations at the same time. I'm going to put different clock recoveries behind these and show you the effects of the clock recovery on those signals. Timing measurements, let's find out what kind of rise times and fall times this signal has. We can do skews between signals, we can do SSC profiles. If you have SSC on purpose in your signals, sometimes you do and you don't realize it, and that can cause the problem because your system's not ready for it, but your transmitter's putting it out. This will draw the profiles and tell you how much there is. Eye diagrams, you can do it with mask hits to find out which bit fails the mask. You can do eye heights. Newer measurements, you can do eye width and eye height at bit error rate, which takes the extrapolation and tells you if you ran this long enough to do a bit error rate, what would your eye opening be? You've got amplitude measurements, and then we have a bunch of standard measurements. And standards, by standard we mean the different standards out there for high-speed serial. We have DDRs, PCI Expresses, SASs, all these different standards, and this is a small subset. What this gives us is the algorithms that are specific to a standard in addition to the algorithms that are general for everybody. So if you picked a standard, PCI Express 3 per se has very specific algorithms they want you to use for measuring those signals. We put those algorithms into our general toolbox here, and you can do all the debug manually and find out everything you need in addition to compliance testing. So let's go back and let's see what we added here. So let's configure. We've now added frequency, and we added TIE2. DPOJET inherits configurations from the channels that the measurements that were already defined above it. So this TIE inherited that clock recovery. I'm going to go turn that clock recovery off, but I'm only turning it off for this measurement. I'll show you why I did that. And then we'll look at rise times, really nothing to configure, fall times, really nothing to configure. results we have none yet, but what I want to do is I'm going to give up this time trend. Currently we offer 4 plots. That will not be the case forever. And I'm going to turn on an eye diagram for this second TIE with the different clock recovery. And let's see if we can tell from the eye if we have a difference in these clock recoveries. Now again, we're going to use the same piece of data. So I'm going to recalculate after adding and changing measurements. That data was critical to me because I triggered it with an error that was in my system. And now you can see why an eye diagram is very important when you're looking at jitter measurements. Do I have an appropriate clock recovery, or do I not have an appropriate clock recovery? Your eye diagram will tell you. That's why you need to see the waveform, the bit shapes, and the eye diagrams all simultaneously when you're working with high-speed serial signals. In this case, we can see that the eye diagram is bouncing between 2 distinct points. And as we saw, there's a 1 megahertz periodic jitter or sinusoidal jitter causing that movement. And we can see a distinct difference between the measurements between the time interval errors with and without that being on. So that gives you a description of that. Now the other thing we did throw in there is what kind of signal are we working with? This is a 28 gigabit signal. You may ask yourself, wait a minute, what scope is he using to have done all of this debug on a 28 gigabit signal? And if you look at the rise times, we're down in the low mid-20s for a mean. We have rise times on this signal as fast as 17 picoseconds. Well, I'm looking at this with a Tektronix DSA 73304D, which is a 33 gigahertz scope. And I'm using a P7630 tri-mode remote sampling head probe to capture it. What that means is I've actually, with this probe, I've got 30 gigahertz out at the probe tip, and all of my measurement reference planes have now moved to the end of this probe where I'm connected up to my device under test. So I do not have to de-embed or go in and simulate anything, because this waveform is what is coming out of my device under test. There are no losses left in the system because I don't have a cable between my device under test and my scope. I have a probe where we've moved the front end out to the end of the probe. So I don't take the noise hit. You can see how clean this is. And I'm looking at a 28 gigabit signal with a 30 gigahertz system. You may have people telling you that you need 50 and 60 gigahertz systems to look at those kind of bit rates. The bit rate is not the thing that's going to be your limiting factor. It's the rise times. If your chips and systems, if your chip characterization, you may have something down on the order of 15 picoseconds or faster. You may even have a chip capable of 10. That's a screaming fast chip. If you do, this scope can still capture 9 picosecond rise times. So we can still capture that. This device under test is putting out 17 to mid-20 type rise times on this signal. I have plenty of bandwidth and capturability in this Tektronix system to debug this 28 gigabit signal. Now, if you're trying to characterize this for your data sheets and parts, you probably want to be using a sampling scope anyway to gain the full resolutions of vertical dynamic range and horizontal accuracies. A Tektronix DSA 8300 has a sub 100 femtosecond jitter noise floor. It has 16 bits vertical. So if you're going to characterize, you need to be using a sampling scope, and the DSA 8300 is the cleanest thing going. If you're going to debug, a real-time scope is often better than a sampling scope, and even at 28 gigabits, the Tektronix 33 gigahertz real-time scope has plenty of horsepower to deal with your 28 gigabit signals in those ranges, as you can see from everything we've looked at so far. I want to thank you for your time, and if you have questions, let us know.